Hi everyone, welcome to the start of our third unit of videos on astronomy. So this is the start of the light and matter unit, and some questions that we're going to consider are: what is light and what kinds of matter make up the universe? Why do stars have different colors? What do these colors mean? And what can a star's light tell us about the star and about the larger universe as a whole? So first of all, actually let's just tackle the first of these essential questions directly. What is light? People have debated this for a very long time, and in modern science the debate is centered between whether it's a wave or a particle. The wave being something propagating through a kind of substance like an ether, or a particle, which would be a particular thing that can be observed all by itself. So Isaac Newton believed that light was composed of small particles. He called them corpuscles, and he believed that different colors of light represented different particles. And he showed that if you use a prism to break white light apart into colors, then a second prism will keep each individual color the same. So this was something that was relatively new. A lot of people give Isaac Newton this big credit for breaking light into colors with his prism and show pictures of him doing that, and people think because of that Isaac Newton was the first person to do this. No, people had been doing this for thousands of years with crystals and stuff like that. But Isaac Newton scientifically investigated these colors by taking a second prism and noting that when you try to break, say, red light into more colors through a second prism, nothing happens. You only get red light. Now, it turns out he was wrong about different colors corresponding to different types of particles. So, in modern times, at least more modern times, 19th century, late 19th century, it was found that if you shine a light source on a solar cell, then the cell generates electricity, or at least at that time it was light on a metal. Nowadays it's solar cells. But in terms of light on a metal, the light will knock out electrons, and these electrons can wander around the circuit and generate electric currents. And the interesting thing about this is that no matter how intense you made the light, some colors of light would do this, whereas other colors would not. So, for example, a relatively dim source of blue light would knock out lots of electrons, and the electrons would have fairly significant energies, whereas an extremely intense source of red light would not knock out anything at all. So there's something weird there. And this seemed to contradict the idea that light was composed of waves, because this whole electromagnetic wave idea, well, the idea is that if you increase the intensity of the wave, it increases the energy of the wave, and greater wave energy should have more energy to knock electrons out. So apparently this was not the case. Einstein showed that this was due to the fact that light is composed of particles. In fact, this was what actually earned Einstein the Nobel Prize in Physics. It was not his discovery of special relativity or general relativity, or the discovery of E equals mc squared, or the realization that basically the proof that atoms exist by his analysis of Brownian motion. It was actually his understanding and his insight into the photoelectric effect, and showing that this means that light must be composed of particles. Now, meanwhile, the wave nature of light. Back in 1678, the Dutch physicist Christian Huygens proposed that light travels in waves, and this was demonstrated by English physicist Thomas Young in 1801, when he took a light source and allowed the light to pass between two thin slits. Now, if light was composed of particles, then on a display board behind the slits you would expect basically two bright spots for the light going through the slits. But instead you got a number of alternating bright and dark bands. Instead of two, you got a whole bunch. And in particular, the middle, where you wouldn't expect to have anything at all because none of the particles should come there, the middle was actually the brightest area of all. So this shows that light is made of particles, because this showed that light is made of waves, because only waves can exhibit interference patterns like this. If I shout at somebody from behind a wall, they can hear me because my sound diffracts around the edges of the wall. So this is what waves will do. Even if it's kind of an open wall with nothing to bounce off of, it'll still diffract around the wall. Waves diffract around edges. And because of this, it's as if each edge serves as a source of the light. So where you get one wavefront hitting a wall at the same time as the wavefront from a different source, you end up getting a bright spot. But if it's the peak of one wavefront hitting at the same point as the trough of another wavefront, then they're going to cancel each other. So that's what's going on with this constructive versus destructive interference and these bright and dark fringes that Thomas Young first noted. What we now realize is that light is composed of a packet of energy. Light is a packet of energy which we call a photon, and this photon has both wave and particle properties. So one way of thinking of this is that the photon itself is the particle. This is what is measured when light actually hits something and causes a detector to fire. And the set of paths that this photon can take is the wave. So you might wonder, it's like, well, okay, back in this double slit experiment, what if you fire the photons one at a time? If you fire the photons one at a time, then you think, okay, it's got to either go through one slit or the other, and you should end up just getting two bright fringes. But it turns out, even when you fire the photons one at a time, you still get, at least when you make a plot of where the detections are made, you get alternating bright and dark fringes. So what this indicates is that, sure, the particle passes through either one slit or the other, but the wave passes through both. And the wave is where the particle can potentially be measured. To add a little bit of eeriness to this, if you try to make a detector to figure out which slit the photon passes through when you fire these one after another, then it turns out that you can detect which slit the photon passes through. It's just that as soon as you do this and you turn on your detector, the interference pattern disappears and you just get two bright areas where the photons are going. So when you try to break down the wave nature of light and figure out exactly which slit it goes through, then the wave nature disappears. That's just one of the results of quantum mechanics. It's found to be true experimentally, and it's also predicted mathematically. Now, in terms of how light acts, the more energetic the light, and at least in terms of the more energetic each individual photon, the more particle-like it behaves. Whereas the less energetic it seems, then the more wave-like it behaves. So radio waves act very wave-like, whereas gamma rays act very particle-like. We'll have more to say about this soon. Now, the speed of the wave, the speed of light. Turns out the speed of light in vacuum is always constant. That's the speed of light. In fact, it is so constant and so reliably constant that the meter is defined to be the distance the light travels in 1/299,792,458th of a second. So you define the SI unit of distance in terms of the speed of light. So you might say, well, is it really in terms of the speed of light? After all, the second hasn't been defined. Well, I'm going to define the second for you very soon, but we need to introduce some other terms. Now, you don't need to know this exact value for the speed of light, but you do need to know that it's about 3 × 10⁸ meters per second, or about 300 million meters per second. Now, we've already had something to say about this wave-particle duality in terms of photons, but other particles behave like this as well. For example, electrons also exhibit waviness when you examine them at very small scales. And this waviness, as it turns out, is going to save us later when we talk about atoms and the stability of atoms. But this waviness has also been measured. Double slit experiments have been performed with electrons as well, and you get these alternating bright and dark fringes. Now, the alternating bright and dark fringes with electrons are much closer together than they are with photons because electrons are more particle-like. The more particle-like something is, the more the wave nature seems to have a very short wavelength. Short wavelength means more particle-like. But nonetheless, they do exhibit this interference pattern. And in so doing, you can therefore state that the wavelength of really anything is equal to Planck's constant divided by the particle's momentum. Now, this works even, for photons. Photons have a momentum even though they don't have a mass, because, as I think I've mentioned before, the official equation, the real equation for momentum, is a little bit different from P equals mv. And it works, the real equation works for things like photons that have no mass, as well as for things like baseballs that do have mass. So, of course, if you have a knuckleball pitcher, baseballs might appear to be kind of wavy in their paths, but that's because of air currents and stuff like that. But in any case, photons, at least visible photons, have wavelengths between 400 and 750 nanometers, as we'll discuss soon. But this means that if you're trying to see viruses, which are typically smaller than this, you need to have something that has a shorter wavelength than this. Well, electrons work very well for this, which is why we use electron microscopes to try to image viruses. So now back to light. James Maxwell, in the late 1850s, started working on really trying to come up with a good theory of the electric and of electricity and magnetism, really. And in so doing, he eventually came up with the so-called Maxwell's equations. And these Maxwell's equations talk about how electric and magnetic fields behave with each other. So, first of all, an electric field is generated by a charged particle. Like charges repel, opposite charges attract. You've learned this a long time ago. A magnetic field is generated by moving charges. In particular, the strength of the magnetic field is going to be proportional to the rate at which an electric field changes. Now also, a changing magnetic field can generate an electric field. In fact, the strength of the electric field is proportional to the rate at which a magnetic field changes. Okay, so let's see what happens if I was to take chopsticks or tweezers and pick up an electron and wiggle it back and forth. Wiggle, 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 wiggle. And I do this sinusoidally. Well, here's the thing. The rate at which a sine function changes is a cosine function. The rate at which a cosine function changes is a negative sine function. The rate at which a negative sine function changes is a negative cosine function, on and on. We've completed the loop now, we're back to sines, etc. So, if I do this sinusoidally, what I'm going to do is I'm going to be generating a sinusoidal electric field and a sinusoidal magnetic field. It's going to become a self-propagating electromagnetic wave. Well, James Maxwell realized this. He was one of the best scientists of his time. And he's like, okay, this generates an electromagnetic wave. Well, that's really nice. Let's just call this electromagnetic radiation. It turns out the electric field is always perpendicular to the magnetic field, by the way, and vice versa. But if it behaves like a wave, then it must correspond to something called the wave equation, a classical physics type equation. And the wave equation, part of it tells you the speed at which the wave is traveling. So when Maxwell kind of compared his equations and noticed that, hey, these look very much like the wave equation. If I just solve for this variable and plug it into for that variable in another equation, then I get the wave equation, where there's something in front of there that must be the square of the speed of the wave. Well, it turned out that when he got his equation looking like this, the thing that was in front of this was 1 over mu naught epsilon naught, where mu naught is something called the permeability of free space, the magnetic permeability of free space, and epsilon naught is the electric permittivity of free space. And lo and behold, when Maxwell plugged in the known values for mu naught and epsilon naught, he found that when he took the square root to get the speed of the wave, it turned out to be equal to the known speed of light. So he said that we can conclude nothing else other than the fact that light is simply another type of electromagnetic wave. So this was the result that Maxwell had from his equations, where in this case his wave function was the electric field, but it also works for the magnetic field as well. So light is an electromagnetic wave. All light, visible light, infrared, X-ray, etc. And all electromagnetic waves travel at the same speed in a vacuum. Now some vocabulary. that we need to make ourselves aware of. First of all is the wavelength. The wavelength is the distance between crests of peak intensity in the electromagnetic wave, whether it's the electric field or the magnetic field part of the electromagnetic wave. The wavelength is the distance between crests, or the distance between troughs. Crests are peaks, troughs are valleys. Now, visible light has a wavelength really between about 400 nanometers and about 750 nanometers. The range 400 to 700 is what's typically given for that, where red light is 700 nanometers and the deepest purple light is 400 nanometers. Below 400 nanometers, just below that, is ultraviolet, and just above 750 nanometers is what we call infrared. But this is just a small part of the overall electromagnetic spectrum. So gamma rays have wavelengths on the order of picometers, X-rays have wavelengths on the order of fractions of nanometers, and ultraviolet rays have wavelengths on the order of tens to hundreds of nanometers. And then we see visible, infrared, on the order of tenths of micrometers, or sorry, on the order of micrometers, that is thousandths of millimeters, and then getting into microwaves on the order of centimeters, and then getting into radio waves with wavelengths on the order of meters, or tens of meters, or hundreds of meters. And infrared, as you'll notice, has actually quite a big range. I mean, we start off with micrometers, but then we're starting to get up to what we call sub-millimeter bands, which, I mean, we have telescopes that can observe in that, which we'll talk about later in this unit. Now, frequency, another vocabulary term that you absolutely must know. So frequency is the number of waves that pass a fixed point in 1 second, the number of wave crests, that is. So 1 hertz is the unit for frequency. It is 1 cycle per second, or simply an inverse second. So if you think about it, let's see, the wavelength is the distance between peaks in a wave. The frequency is how many peaks pass by per second. So if I was to multiply the wavelength and the frequency, what I would have is the distance traveled by the wave per second. Well, that's called the speed. So the speed of any wave is equal to the wavelength times the frequency. Now, the symbol for frequency of the electromagnetic waves is the lowercase Greek letter nu, like nu. Instead of knights who say ni, it's like knights who say nu. So if it's not an electromagnetic wave, wave frequency is often given by the symbol lowercase f, but if it is electromagnetic, then we often use the lowercase Greek letter nu. So one of the oldest jokes in science is somebody walks into a room and says, "What's new?" The person replies, "C over lambda," where lambda is the symbol for wavelength. And c, of course, is the speed of light. Now, make absolutely sure you do not confuse nu with the velocity v. The symbols do look kind of similar, but they should not be confused, especially since the Greek nu is their version of our letter n. Of course, they would say that our n is our version of their nu, because they came first. Anyway, so the energy of a wave packet, that is a photon, is given by the frequency nu times h, where h is Planck's constant, which is about 6.626 times 10 to the minus 34 joule seconds. It's actually a unit of angular momentum. So with that in mind, that means that higher energy means higher frequency and shorter wavelength. So short wavelength is like, okay, this is very particle-like. That corresponds with high energy, high frequency. Whereas long wavelength, this is more kind of wave-like. This corresponds with low energy and low frequency. So radio waves, I mean, they can have thicknesses on the order of meters, which is why they're able to get through walls and why you're able to listen to the radio indoors. So just some other representative wavelengths in the electromagnetic spectrum. So notice, of course, visible, and then their corresponding frequencies and stuff like that. So quick practice with each other. So you might want to pause the video, thinking about this real quick, just a quick test. What has the longest wavelength, highest energy, and highest frequency in these 3 examples? So it might be a good time to pause now, give you a few seconds. Okay, so if you have either skipped pausing or have unpaused, for the longest wavelength between infrared, that would be the infrared. Because X-rays, you know, they're very short wavelength, high energy. That's why they're able to power through skin, though they're not quite powerful enough to power through bone, which makes them useful for making X-ray pictures. The highest energy, gamma rays, have the highest energy of all. Gamma rays have the highest energy of all. That's why they are so dangerous, because they can power their way through your cells and destroy cell nuclei and stuff like that, which can cause mutations. And how about the highest frequency between infrared and radio? Well, radio waves have the longest wavelength, which means they have the lowest frequency of all. So infrared waves, or infrared light, has higher frequency than radio waves. Now, what about Earth's atmosphere? How do these different types of electromagnetic radiation get through Earth's atmosphere? Well, as we know, visible light gets through. That's good, because we see in visible light. That's also good, because our sun emits probably most of its energy in the visible part of the spectrum. Now, infrared light, some of that gets through, but not all of it. A lot of it gets absorbed by our atmosphere. And I'll give you a time to think about something. Which compound in our atmosphere do you think is most responsible for absorbing infrared light? In other words, what is it that provides Earth with most of its greenhouse effect? So we're going to come back to that soon. Ultraviolet gets partially through the atmosphere until it gets absorbed by ozone. So it's a good thing that that gets absorbed, because ultraviolet is high energy and that can cause cell damage. X-rays, fortunately, also get absorbed, as do most gamma rays. Though some gamma rays are able to kind of power their way down into the atmosphere. Gamma rays are kind of like bullies. Now, radio waves, some of those bounce off the atmosphere. They don't get absorbed, they simply get reflected, especially if they're coming in at any angle that's not like 90 degrees. So, shorter wavelength radio can actually penetrate through, which has some interesting consequences. In fact, one of the more interesting of these consequences is the fact that, think about FM versus AM radio stations. Which type of radio station can you listen to over a longer distance farther away from where it's being transmitted from, FM or AM? Turns out you can listen to AM radio stations over a much greater distance than FM, because FM waves get absorbed by our atmosphere, but AM waves bounce off of the atmosphere. So since FM is absorbed and thus doesn't end up coming back to the surface, once you get out of range of the radio station, in other words, once you've gotten far enough away that the radio station has disappeared over the horizon, or once the antenna has disappeared over the horizon due to Earth's curvature, you're out of reach of that radio station. However, AM can go much farther, because the AM waves can bounce off of the part of the atmosphere that's about 60 miles up, the ionosphere, and then bounce back toward the surface, which is why some AM stations can be listened to like hundreds of miles away. So it's a really cool effect. So there's our radio window and the visual window. Now, as we already mentioned, ultraviolet is absorbed by ozone. Infrared is actually mainly absorbed by, surprise, surprise, water vapor. Most people would probably say carbon dioxide in this, because you hear all kinds of stuff about carbon dioxide in the news. But actually, the vast majority of our greenhouse effect is caused by water vapor in the lower atmosphere. The reason people are concerned about carbon dioxide, of course, is because we are increasing the amount of carbon dioxide. So even though carbon dioxide is considered a minor greenhouse gas, the fact that its amount in the atmosphere is going up could end up causing some what could be disastrous effects if it ends up going up a bit too much. But we'll have more to say about that in a later unit. Now, in terms of astronomy, one of the problems about infrared getting absorbed is that infrared telescopes don't work too well on Earth's surface. However, you can put infrared observatories high up on mountains, and that gets above most of the water vapor, as well as in airplanes, or even better, in space. So for example, the Keck telescopes right here, they have the ability to observe in at least the near infrared. When I say near infrared, I'm talking about the infrared part of the spectrum that is near visible. And here's an example of the Sophia Observatory where they have an infrared telescope in a 747. And just open the panel here and make your infrared observations. The Hubble Space Telescope has infrared capabilities. It's mainly a visible light observatory, but it does have infrared capabilities. It also has ultraviolet capabilities. So it has many capabilities. The James Webb Space Telescope, which some people call the successor to Hubble, but in truth is going to be more of an infrared observatory. That's going to be a larger telescope, but it will mainly observe in the infrared, and it will be an orbiting telescope just like Hubble. Now, the radio band, the kind of near the FM part that gets through the atmosphere, well, that's what radio telescopes can observe. So, how do we measure electromagnetic radiation? One of the most common ways of measuring it is in terms of the rate at which we are getting energy from it if we are using a detector. And then we can kind of trace that back to think about how much electromagnetic radiation is being emitted from the source. And that is known as its luminosity. Luminosity is the rate at which energy is being emitted. The units for luminosity are watts, where 1 watt is a joule per second, where the joule is the SI unit of energy. So like we talk about 100-watt light bulbs or 75-watt light bulbs, that simply means a light bulb that is emitting 75 joules of energy every second. In comparison, the luminosity of our sun is about 3.8 times 10 to the 26th watts. So that would be 3.8 trillion 100-watt light bulbs. In addition, light propagates in accordance with the inverse square law if it's coming from a source that's spherically symmetric, like say a star or a point source. What we mean by that is that the brightness decreases as the square of the distance. So if we move twice as far away, then it's going to be 1/4 as bright. 3 times as far away, 1/9 as bright, etc. You can kind of see that in this diagram here, where if you have some source of light, you can imagine surrounding it with a sphere of some radius, and a certain amount of light will go through a kind of cone at a certain point on that sphere. Well, that same cone is going to end up being twice as wide in each dimension for a sphere that itself has twice the radius. In other words, if you're at a point that's twice as far away from your light source. So that light, that same amount of light, has spread into an area that is now 4 times the area as before. But it's the same amount of light, which means that each spot will only receive 1/4 as much light as before. And similarly, if you're 3 times as far away, that gets spread out into a dimension that's 3 times as big in each direction. So that means that gets spread out into 9 separate squares, so each square receives only 1/9 as much light. Those of you who are familiar with more advanced physics will see a very nice analog with Gauss's law here. In fact, guess what? This is Gauss's law. So the result of this is that anything that emits anything like an electric field, light, a gravitational field, or something that is spherically symmetric, you're going to have a 1/distance squared relationship in terms of the field strength, or in this case, the intensity. So brightness goes as luminosity divided by distance squared. So certainly, if you take a brighter source, it's going to appear brighter. But if you get farther away, it's going to appear dimmer. If you get closer, it's going to appear brighter. So something that's twice as far away is going to be 1/4 as bright. Now, when astronomers use the term brightness, what they're actually often referring to is something called flux, which is power per square meter. Or think of it as how many joules of radiation fall on a square meter every second. So in order to determine the flux, which is basically how bright something looks, you simply take the luminosity and imagine spreading that out over a surface that completely surrounds the source. Well, since the source is usually like a star or something else that's spherically symmetric, your surface would be a spherical surface. So, well, the area of a sphere is 4 pi r squared, so the flux is equal to the luminosity divided by 4 pi r squared, where r is the distance from the center of the source. So there's kind of a direct example of that 1 over r squared force law, because we see it in this actual quantitative measurement of the flux. So the farther you are, the dimmer something's going to look. But the brighter it is, the brighter it's going to look. Now, just a summary of what we've discussed so far. Visible light is a form of electromagnetic radiation that includes an order of increasing wavelength, and thus decreasing frequency and decreasing energy. Gamma rays, which are the most energetic, then X-rays, ultraviolet, visible, infrared, and radio. And a lot of people put microwaves between infrared and radio waves. It consists of electromagnetic radiation consists of alternating electric and magnetic fields, and these travel in vacuum at the speed of light, which is about 3 times 10 to the 8 meters per second. Earth's atmosphere is transparent only in a few places, one of which happens to be the visible part of the spectrum, fortunately for us. And light can behave as both a wave and as a particle. This is something that we're going to come back to occasionally in this course. The wave packet of energy is called a photon. The more energetic the packet, the more particle-like it is. That is, the shorter the wavelength, the higher the frequency. And brightness of a source drops off as 1 over distance squared. So you don't need to memorize the formula F equals L over 4 pi r squared, but you do need to know the brightness drops off as 1 over distance squared. So that's the summary of what we have so far. In the next video, we're going to start to talk about matter, the different phases of matter, and how things are in terms of matter in the universe. So I hope to see you then, and thank you for watching.